A warm welcome to part 6 of the lecture on functions. In the previous lecture, we learnt about even and odd functions. In this lecture, we will study periodic and aperiodic functions. This will probably be the first part on periodic and aperiodic functions. The word periodic in day-to-day usage means something which repeats itself after a regular interval of time. The mathematical notion of a periodic function is exactly the same. So let us formalize it. Let f be a function from R to R. F is said to be periodic if there exists a real number t strictly greater than 0 such that f of x plus t is equal to f of x for all x belonging to R. T in such a case is said to be a period of f. It is also worth mentioning that t must be a constant that is independent of x. Later on we will consider an example where we will find out that if t doesn't happen to be a constant, the function indeed becomes aperiodic. If t is a period of f, then so is nt. This means f of x plus nt is equal to f of x for all x belonging to R. N is a natural number. I will prove this result only for a special case n is equal to 2. For a general n, one can resort to the principle of mathematical induction, and it is indeed not a very difficult exercise to carry out yourself. F of x plus 2t is equal to f of x plus t plus t. Now since t is a period, by the very definition we can conclude that f of x plus t is nothing but equal to f of x plus t. But f of x plus t is equal to f of x for all x belonging to R. Therefore, we conclude that f of x plus 2t is equal to f of x for all x belonging to R. This implies that 2t indeed is a period of f. An immediate conclusion is the following. The period of a periodic function is not unique, as we have just seen, because if t is a period, so is 2t, so is 3t, and so on. This brings us to a fundamental definition called the fundamental period of the periodic function. If t naught happens to be the smallest positive number for which f of x plus t naught is equal to f of x for all x belonging to R, then t naught is said to be the fundamental period of f, which means there should not exist any positive number smaller than t naught for which the function, so to say, repeats itself. There is a very important remark which I should make at this point, that the fundamental period need not always exist for every periodic function. Specifically, we will look at two counter examples of periodic functions which do not admit a fundamental period. The first example is that of the constant function. F of x is equal to c for all x belonging to R. Is f periodic? The answer is yes, because for any t greater than 0, f of x plus t is equal to c, because after all f is a constant, and c is equal to f of x. So we can conclude that f of x is equal to f of x plus t for all x belonging to R and for any t greater than 0. So f is periodic. Now the question is, what is the fundamental period of f? The fundamental period, if it exists, must be the smallest positive number for which this relationship f of x plus t equal to fx should hold. It turns out that in this case the fundamental period does not exist, and the reason is the following. If t greater than 0 is a period of the constant function, then so is t by 2, because we have just seen that the relation f of x plus t equal to f of x holds for any t greater than 0. So if it holds for t, it should also hold for t by 2. This brings us to the conclusion that there does not exist any smallest period, because if you give me any positive number t, I will just divide it by 2 to get a smaller positive number which still acts as the period. Therefore, there is no smallest period, and hence no question of fundamental period in this case. Let us consider another example. F is a function from R to R given by the following rule. F of x is equal to 1 if x is a rational number and 0 if x is an irrational number. The first question is the following. Is f a periodic function? The answer is again yes. Let us see why is that. Let q belong to the set of positive rational numbers. So basically q is a positive rational number. My claim is the following. F of x plus q is equal to f of x for all x belonging to R. That is, any positive rational number serves as a period of this function. Let us see a proof of this. First, let us assume that x itself is a rational number. So in order to prove that q is a period, we must show that f of x plus q is equal to f of x for every x belonging to R. We will split the proof into two cases. First, when x is a rational number, that is x belongs to q, and the other case when x does not belong to q, and we will finally show that in both of these cases this particular equation holds true. So that is our agenda. So first we will consider that x is a rational number, x belongs to q. If x belongs to q, then x plus small q, that is the rational number which we have considered as a period, x plus small q must also be a rational number because the sum of two rational numbers is a rational number. This implies that f of x plus q is equal to 1, and this is equal to f of x because we have chosen x to be a rational number and f takes value 1 at all rational numbers. So we conclude that if x is a rational number, then f of x is equal to f of x plus q. Let us consider the other case when x is an irrational number. If x is irrational and small q as before is a rational number, then x plus q must be irrational. Why is that? Let us prove this by contradiction. Suppose x plus q is not irrational, then it must be equal to some rational number, say p, which means x is equal to p minus q because x plus q is assumed to be equal to p where p is a rational. But now x is the difference of two rational numbers and therefore x must be rational. Now this is a contradiction because we have started off by assuming that x is an irrational number, and therefore x at the same time cannot be both rational and irrational. Therefore our assumption that x plus small q is a rational number is false, and therefore we conclude that x plus q must belong to the set of irrationals. Now since x plus q is irrational in this case, therefore f of x plus q must be equal to 0, and this must be equal to f of x since we had chosen x to be irrational. Therefore in this case also, when x is an irrational number, we conclude that f of x plus q is equal to f of x for all x belonging to R and any q belonging to the set of positive rational numbers. We asked the same question, what is the fundamental period of f? As before, the fundamental period in this case also does not exist because there is no such thing as the smallest positive rational number. For example, if you give me any rational number, any positive rational number q, I can divide it by 2 and get q by 2, which is also a positive rational number. Therefore, the concept of the smallest positive rational number does not arise. Hence, the fundamental period of this function also does not exist. Now, let me make a couple of remarks. The first is the following. Being periodic does not guarantee the existence of the fundamental period, as we have just seen by means of two counterexamples. The other remark is the following. If f is a periodic function with period t, then knowing the function value at every x belonging to a particular period, be it the closed interval 0, t or the closed interval t, 2t or any other single period, is enough to know the function values at any other x belonging to R. So basically the entire information about the function f, which is periodic, is captured in a single period of the function, and that same information is just basically translated throughout the real line. Let us argue rigorously why is this true. Why is knowing the function values only in a single period sufficient to know the function values at all other values of x? We can argue as follows. The whole real line R can be expressed as a disjoint union of semi-closed intervals of the form nt, n plus 1t, closed at nt and open at n plus 1t, where n belongs to the set of integers. So basically, the whole real line has been, so to say, partitioned by these semi-closed intervals. So 0, t, t, 2t, 2t, 3t, etc. All these semi-closed intervals partition the whole real line. Therefore, any x belonging to R belongs to exactly one of these intervals, because these intervals which are partitioning the whole set R are mutually disjoint. So any x can belong to at most, in fact, exactly one such semi-closed interval. We assume that f is known in one of the intervals, say the semi-closed interval 0, t. Now let x be any real number. So let x belongs to the semi-closed interval mt, m plus 1t, where m is some integer. This means that mt is less than equal to x less than m plus 1t. Now if you subtract mt on all sides, you get 0 is less than equal to x minus mt is strictly less than t. Now notice that this number x minus mt belongs to the interval 0, t in which my function is known. Now x can be written as x is equal to x minus mt plus mt. Therefore f of x is equal to f of x minus mt plus mt. And by virtue of periodicity, this is just equal to f of x minus mt. So the value of f at any x belonging to R is known precisely in terms of the value of f in a particular interval, in this case 0, t. So f of x is equal to f of x minus mt, where, as we have seen, x minus mt belongs to the semi-closed interval 0, t. How does this fact manifest in the graph of f? The graph of f restricted to any periodic interval, say mt, m plus 1t, where m is an integer, is just a translate of graph of f restricted to 0, t. So that means if you know the graph of f in a particular interval, say 0, t, you can just simply translate it by a suitable number m to obtain the graph of f restricted to any other interval of the form mt, m plus 1t. In this way, the graph of f restricted to, say 0, t serves as a building block for the graph of f over R, because basically this particular block is simply translated throughout. This is exactly what we mean when we say that the graph of a periodic function repeats after every period. Now let us consider some more popular example of periodic functions. As a first example, consider the sine function from R to R. X goes to sine x. We all know that sine x is a periodic function with period 2n pi, where n belongs to the set of natural numbers. The fundamental period of f, which in this case is the sine, is 2 pi. This is well known from our knowledge of basic elementary trigonometry. And the graph of f looks like this. So what is worth noticing is that the graph of f over a period, say 0 to 2 pi, is a building block which repeats itself after every period of 2 pi. From minus 2 pi to 0, we have this particular shape, And the same shape now just repeats itself for other periods also. As a second example, consider the cos function. In case of cos also, the period is 2n pi, where n is a natural number, and the fundamental period is again 2 pi, and the graph of cos x looks like this. So again, the graph of cos x over a particular period 0 to 2 pi is repeated time and again. Consider a tan function defined on r minus 2n plus 1 pi by 2, where n is an integer, because the tan function is not defined at points like pi by 2, 3 pi by 2, etc. So we are excluding all those points from the real line. Now tan is, as we all know, a periodic function with period n pi, and the fundamental period of the tan function is pi. And the graph of the tan function looks like this. So again, I urge you to notice that the particular building block, which is the graph of f in one particular period, so minus pi by 2 to pi by 2, is repeated throughout. Finally, let us consider the function which is called the fractional part of x. It is a function from r to r, and it is defined as fractional part of x is equal to x minus greatest integer function of x minus step of x, as they say. So this function is actually a periodic function, and the period is n, where n is any natural number, and the fundamental period is equal to 1, because 1 is the smallest natural number. It is very easy to check why this fractional part of x is periodic with period n. If you just replace x by x plus n, you get fractional part of x plus n will be equal to x plus n minus greatest integer of x plus n. Now greatest integer of x plus n is equal to greatest integer of x plus n. So finally, this n and minus n will get cancelled, and you will be left with x minus greatest integer of x. So fractional part of x plus n, which is this, is equal to fractional part of x. Therefore, the fractional part of x as a function is periodic with period n, and the fundamental period is equal to 1. The graph of the function, the fractional part of x, is same as this, as shown in the figure. Let me wind this lecture by assigning you two simple exercises which are pretty straightforward to work out. So if f is a function from r to r which is periodic with fundamental period t0, then g from r to r such that gx is equal to f of x plus c, where c is a constant, is also periodic with fundamental period t0. So basically you have to show that if f is a periodic function with fundamental period t0, then gx defined as f of x plus c is also periodic with the same fundamental period t0. The second exercise is the following. If f from r to r is periodic with fundamental period t0, then the function g from r to r defined as x goes to f of omega x, that is g of x equal to f of omega x, where omega is any non-zero real number. We have to show that gx equal to f of omega x is also a periodic function with fundamental period given by t0 by mod omega. As a corollary to the previous exercises, which I have left to you to solve for yourself, we can immediately conclude the following. The functions sin x plus c, cos x plus c are also periodic with fundamental period 2 pi. Tan x plus c has fundamental period pi. Similarly, sin omega x and cos omega x have fundamental period 2 pi by omega, where 2 pi by mod omega, where omega is any non-zero real number. And finally, tan omega x has a fundamental period pi by mod omega, where again omega is a non-zero real number. as you can see. I'll end this lecture now. In the next lecture, we will see some examples of aperiodic functions, and finally we will move to the study of the sum of periodic functions, where all kinds of weird things begin to happen. We will study those things in a fair amount of detail, but largely the proofs of many results will not be given as they are beyond the scope of the discussion. Thank you.